Alright, so hi everyone. So this is session 15, and we will continue the discussion of normal distribution. And before we move on to any new topics, I do want to go over the normal distribution that we properties and some characteristics of normal distribution. So let's just go ahead and do this first, right? So okay. Just give me a moment. Alright, so normal distribution, as I mentioned previously, is this is the single most important distribution in statistics. And the reason why that is the case is because if you have any kind of distribution, whether it's binomial or even if you're not sure of the distribution, if you have a large n, then it will become more and more normal. Alright, and we will discuss that later with the law of large number, but that's the case for any distribution, so any distribution, if you have large n, you will have a normal distribution. That's why it's so powerful. And normal distribution is also known as Gaussian or the bell curve, and the reason being is it looks like a bell curve. Okay, so this is f of x, and we mentioned that this is a PDF of normal distribution. PDF of normal distribution, you don't really have to know, but I guess it's the formula looks as follows. E to the negative x minus e. Okay, so this is a formula for the PDF, right? And we discussed that when we are looking at the probability, it's always the area under the curve. So say that, okay, so probability is the area under the curve. So if we're looking at something like probability of x being in between a and b, that's going to be this area right here. Okay, so this is the area and this corresponds to probability of x being between a and b. Okay, and if you know calculus, if you know integration, this is actually the integral of integral of a to b of f of x dx, but we're not going to deal with calculus as much, because we do have other tools such as Excel or table, so we can approximate this value using those tools given. Right? So you just have to know that the area under the curve represents the probability. Right? And we also learned the z-score, the standardized normal distribution. We denote this as the following, because mu for any standardized normal distribution is 0, and sigma is always 1. So it's like this. Mu is always 0, and standard deviation is 1. So we can use this, so we can transfer any normal distribution to approximate probability. Okay, and this is something called z-score. Right? This is how we standardize this: x minus mu over sigma. And again, x minus mu part, this part corresponds to shifting the center towards 0. Okay, so this is shifting the center to 0, and sigma, dividing by sigma, rescales the distribution. So it can make it wider or narrower. Okay? And we also learned that probability of, if you have a standardized normal distribution, probability of z is less than or equal to a little z. This is denoted as phi of z. Okay, and we can refer this back with a table, z-score table. Alright, I believe the table was included in the class material, so you can, if you didn't know that, you can just download it. It's no big deal. You can just Google it, it will come up. Alright, so that's that. And also, this is something not necessarily new, but if you think about it, if you have a table, you can look up the probability in order to get z-score, right? So let me just pull up the table. Alright, so this is the normal distribution table. So say we're looking at and again, this is the standard version, so standardized normal distribution. Right? So for example, if you're looking for probability that Z is less than or equal to I don't know, 1.76, then you would go 0.7, right? And this column right here. So the answer is 0.7764. Okay, so that's how you would find the probability, and you can do the inverse. So if you know what the probability is, then you can look for the z-score. So for example, say we're looking for percentiles, and what does percentile represent? So say we're looking for I don't know, 75th percentile. Okay, and we can denote this value as x. Then this means that everything no, let's just say this is 8. Everything up to 8 has probability of 0.75. So everything up to that number, including that number, is at least 0.75, right? So we can do the inverse. We can look at the flip side when we have the probability, right? So we can try to look for 0.75 as close as possible, and I would say it's somewhere here, right? It might be right in between. So if you go through this is 0.6, and it's in between 7 and 8. So I would say approximately that z-score would be 0.675. Okay, and this would be helpful because when we're looking at percentiles, again, z is x minus mu over standard deviation. So if you know the z-score, say z-score is this, and we're looking for the percentile, then we were looking for x, and we have mu and sigma, right? So you can just solve for x, and this would be the 75th percentile. Right, so you can go back and forth with this. Alright, so okay, so let's look at an example. Okay, say this is, I believe we work on this example yesterday, but we can use this again. So say that x is normally distributed with mean of 60 and standard deviation of 4. Okay, and we are looking for our let me just do 60th percentile. Okay, so first we need to find the z-score. So we can do that here. The percentage has to be greater than 0.6. So looking at 0.6. So 0.6 is right here. So that's going to be 0.26. Okay. Okay, so z-score is 0.26. Z-score is 0.26. And we're looking for the x value, so C is always x minus mu over sigma. X minus mu, in this case 60 over 4. Okay, so if you multiply this out, you will get a value for x, and that is going to be, let me just quickly do this, 4 times 0.26 plus 6. This is going to be right, so that's the answer. Alright, so that's how you would determine percentiles. And now we're going to talk about something not necessarily new, but something relevant to what we learned before. Okay, and that's approximating binomial distribution. Alright, so we're gonna see how normal distribution is used to approximate binomial distribution, right? So, let's just recall something. Recall binomial distribution. Oops. Okay. Okay. So binomial distribution is having two two possible cases, and one is success and one is failure. And for binomial distribution, we have two parameters, and that's n and p. N represents the number of trials. Okay, this is getting weird. Okay, so n represents the number of trials, whereas p represents probability of success. Okay, and another thing, so expected value of binomial distribution is always n times p, and variance variance of x for binomial distribution is always n times p times q. Okay? So, keeping this in mind, let's just look at how normal distribution is used. Alright, so just going back to the simulation that we had, I just wanted to show you something. So let's see. Alright, so this is something that we didn't learn yet, central limit theorem, but I believe we will have time to do this. This is very important, central limit theorem. So it pretty much shows how binomial distribution converges to normal distribution, and when n gets really big, right? And let's look at this. So if n is, I don't know, n is 1, then this is not a good approximation to normal distribution. But as you increase n, see, this is only 33, and it's starting to look like normal, very close to normal, right? And if you increase it, this is, I'm going to 200 right now, and if you bring it up to 1000, this is the normal distribution, right? So we do use normal distribution to approximate the value for binomial, right? And we're going to look at this, so I'm just going to click this. Alright. So let's look at this. Alright. So using normal distribution is widely used using distribution to approximate binomial distribution. Okay, and there is something that you need to know. When we use it when these conditions are met. Okay, so the conditions are as follows. First is when n is large. Okay, and by large we mean 30 or more. Okay. Sometimes textbook noted as the following: when n times p is greater than or equal to 15, but these are about the same. And I would say n greater than 30 is more of the conventional way to go. And when when p is not close to 0 or 1. So it's not at the extreme. If it's around the middle range, then it's okay. Okay? So these are the things that you need to be aware of. When using normal distribution to approximate. Okay, so Yeah. So let's look at this. So how to use normal distribution? We pretty much use the same thing. We use z-score to approximate, and then get the probability using the table or Excel function. But in a nutshell, it goes as follows. So, and we know that expected value of binomial is n times p, and variance is npq. Correct? We replace mu, which is the population mean, with the expected value, which is np, and sigma square with npq. Okay, so let's look at an example and see how this works. Okay, so let's look at this. Right, so a die is rolled 2,880 times. Okay, and find the probability of obtaining between probability of obtaining between 450 and 500. Okay, so let's assign some random variables. So x represents 100 aces. Okay, number of aces. Alright, and n is given as 2,080. Right, these are the independent trials, and we first of all, it's greater than 30, so it is safe to use normal approximation. And the probability we're looking for is x is in between these two values. Okay, and using the normal approximation, we know that we can replace mu with n times p, and sigma square with npq. So n times p is n times p. What's the probability of getting an ace? Well, there are 6 sides, and ace is just one of them, so it's 1 out of 6. So n times p would be 480. And for sigma squared, it's n times p times q, so n times p times q. So this is going to be 400. Okay? And if we're looking for sigma, that's going to be just 20. Okay? So transferring this into standardized normal, we have to make these into z-scores. So what we're going to do is we're going to, again, z-score is x minus mu over sigma, right? So this is x minus mu is 480 over sigma is 20. 500 minus 480 over 20. Okay? So if you calculate this, you're going to get negative 1.5. And now this is z. And here is 1. Okay? And using the table, we can find this. This is phi of 1 minus phi of negative 1.5, which is phi of 1 minus 1 minus phi of 1.5. Okay. Phi of 1.5. Okay. So this comes out to be phi of 1 plus phi of 1.5 minus 1. Okay, so let's look at the table. I'm not sure if I have the table here. Alright, so this is a table. And we're looking for phi of 1 and phi of 1.5. So phi of 1 is 8413. Write that down. And phi of 1.5 is 9332. And minus 1. There's my minus 1. Right, so if you calculate that out, that's going to be 0.7745. Okay, so that's pretty much how you would use it. But there is a problem with it. Why? Because let's go up and look at the graph. Okay, why is it not going up? Alright, so let's look at this graph right here. And notice that this is the standardized normal because we have mu equal to 0. Say we're looking at probability. Probability of z greater than -2. Okay? And if you're looking at the graph, you might notice that, okay, so if we're doing z is greater than -2, we're just doing this part. Right? From all the way here to all the way to the end. Right? And notice that when we're doing this, the real binomial is the histogram. We're leaving these parts out. These parts. And how do we calculate this? Well, that is why when, oh, sorry. This is called continuity correction. So what we do here is we take it from here, the value. So we are actually going to include this part as well. Okay, and this part. Just this part. Oops. No. Okay, so, and I will explain a little more why that is the case. Okay, it's not listening to me at all. Alright, so let's go down and let's write it down. We call this continuity correction because, as you remember, binomial distribution is discrete. Meaning it's not continuous. You have a value at a certain point, right? But normal distribution is not the case. Normal distribution is continuous. So here we have binomial. This is discrete. And we have normal. This is continuous. So for discrete values, we do have probability that x is equal to little x, but for continuous, we don't. This is correct, but we don't have anything like that. This is 0 for normal distribution. So we take into consideration anything that rounds to that value. So what I mean by this is the following. So for example, if you're doing x is greater than or equal to 2, okay, then we are actually including 2. So what I'm trying to point out is that this, okay, in normal distribution, this is the same thing as this, because essentially x equal to 2 is 0, so these two are the same. But in binomial, this is different. Binomial has a value on, it might have a value on x equals 2. So we have to take that into consideration. So whenever we have that equal sign underneath, we would change this to probability of x greater than 1.5. So which means that anything, if you think about it, anything greater than or equal to 1.5 rounds up to 2, right? So we're doing anything that rounds up to 2, we're just going to include them because this is continuous and we're trying to figure out a way to transform this into a discrete. So that's something called continuity correction. Okay, so let's look at an example. Okay, so here is an example. This is a binomial distribution. Example. N equals 16 and P equals 1/2. Okay? And we're going to do this 2 ways. Alright, yeah. We're going to do this 2 ways, alright? So this, although the n is a little smaller, we're just going to compare and see what the errors are when we're using normal distribution. Okay, so n equals 16 and p equals 1/2. Find the probability of getting between 5 and 10, right? So 5 and 10. This is what we're looking for, okay? So we're going to do this first exactly by binomial, okay? So binomial. Oops. And I will show you how to do this. I mean, there are ways of doing this manually, but at this point, it's not that important, right? If you have any other technology that we can make use of, then we can definitely use that. So I'll show you how to work this on Excel, and I'm going to fix this where it's not working. So I'm just going to write binomial. By binomial, right? So if it's greater than or equal to 5 but less than or equal to 10, oops, sorry, it's listening to me again. Okay, I'll show you how to do that on Excel, right? So let's move on to Excel. Okay, so now I'm going to show you how to do this on Excel. So first of all, we're just going to simply use the binomial distribution to get the exact value, right? So what we're going to do is, here we're going to use something called binomial distribution function. So these are already built in Excel, so you don't have to do anything. Just equal and binom dot dist. And oh yeah, before we do that, I'm just going to write what we're looking for before we do that. Okay, so it's going to be probability of, I don't know why it's not working. Alright, so it's not working, so I'm just going to type it. Okay, so it's this. We're looking for the probability, right down here, probability that x is greater than or equal to, was it 5? Yeah, so greater than or equal to 5, but less than or equal to 10. Okay, so this is what we're looking for. And there is a function for this, and that's if we're looking for a range, right? So that's going to be binom dot this dot range, and it's simple. Open parentheses. You have to put in the trials, which is n, so 16, and probability. Those are the parameters of binomial distribution, so 0.5. And number 1 and number 2. So just give it a range, and it will give it to you. So it's going to be 5 and 10. And binomial distribution range function includes those endpoints. Alright, so if you do this, it's going to give you this, greater than or equal to and greater than or equal to. So it's going to include 5 and 10. So the answer we get is this, 0.8565. Alright, so this was using binomial distribution, and I just wanted to show you how you would do this without using the range function, because we do have just binomial distribution. Okay, if you do this, it's going to ask for a number, trial, probability, and cumulative. Alright, so what it's going to do here, if you put in 5, right, 5, 16, probability will be 0.5, and cumulative, you just write true. Okay, if you do that, it's going to give you a value where this corresponds to probability of as x is less than or equal to 5. Okay, so if you put in 5, it's going to give you every probability up till 5, including 5. Okay, so it gives you probability of that. And if we're using this to figure out this range, then you would have to think a little, because it only gives you one range, and if we were doing this 2 ways, you would have to do probability of less than or equal to 10, but that gives you a little problem here. So let's just look at this. Binom dist, it's going to be numbers 10, 16.5, and true. And if you subtract these numbers, this does not correspond to the one that we got, right? If you think about it, if we're subtracting 10 probability including 10, I'm sorry, if we're subtracting this from that, then it's going to also subtract x equals 5, right? But we want that included, so instead of doing this, we would have to change this to 4 in order to have 5 included in the range. Okay, so here we're going to change the 5 to 4. If you change that, you'll get the same answer as that. Alright, so that was that. Part B is via normal distribution. So first of all, we have to find mu and sigma, what to replace with. So mu is n times p. N times p equals we have n here times p, and this is the mu that we're going to use. Okay, and sigma is n square root of n times p times q. So sigma is square root, again this there is a function for us, so square root and n times p times q. So n times p times q is 1 minus p. And if you do that, sigma is 2. Okay, so we're going to use these numbers to do this via normal distribution, and this is without, let me just write that down, without continuity correction. Okay, so this is simply going to be probability of x is greater than equal to or greater than, it doesn't matter because normal is always the same, and 10. And for normal distribution, we use the following. It's almost the same, but it's going to be norm dot dist, and this again gives you the cumulative distribution function, which I mean everything. If you select a point, a number, it's going to give you areas under the curve up till the point. So probability of less than or equal to that point, right? So x in this case would be 5, and it doesn't matter if it includes 5 or not because this is a continuous case, and mean is 8, standard deviation is 2, and cumulative says, so it's true, it should be true. Okay, if you do that, this is let me just bring this down here. So this is probability of x less than or equal to, or less than 5. oops, that's greater than, sorry, x. Okay, and we're going to do the same with 10. And if you subtract these values, you're going to get this. Alright, so we're going to do the same. Norm dot dist. The number here is 10. Mean 8. Standard deviation 2. Cumulative true. Okay, this is the value we get. And if you subtract those two, subtract this, this is the answer we get. Okay, let me just highlight these. Alright? And now, lastly, we're going to do this using continuity correction via the normal with continuity. Okay, so this is going to look like this. So essentially it's looking for 5, including 5, because we're changing the well, we're counting the including points, right? The endpoints. So this is what it looks like. And let's look at this, how we would do this. This is you would have to include any point that rounds up to 5 and 10. So this is going to be probability of 4.5, greater than 4.5, and less than or equal to, or less than just 10.5. Right? So doing this, we're going to combine this time, so it's going to be normal dot dist. We're going to do 10.5 side first, so that's going to be 10.5. Mean is 8. Standard deviation is 2. Dot true. And then we have to subtract the 4.5 part. So norm dot dist again. This time it's 4.5 times NP, standard deviation, and true. And we get this value. Okay, and let's see how they compare. Right? If you look at this and that number, this is the correct exact value, and this is the normal with continuity correction. It's very, very close. Right? It's only 0.002 apart, approximately. And if you look at this, normal without continuity correction, this is pretty far off. And actually, it's really good because n here is only 16, and we get this much closer to the real value. So this is why we use continuity correction for binomial whenever we're counting for it. Okay, so let's go back to that. That was example we used, and let me just write down the Excel function just in case you might want to refer back to it. Okay, so for Excel, for using binomial, we use binom.dist. You put in the number, so x. Here is n, p, and here you put true or false. Okay, depending on what you want. So if you put in true, this is going to give you the cumulative. Okay, and this is exact value. Alright, so for example, if you're looking for probability of x is 2, then you're just going to put in binom.dist, put in 2 and p and false, then this is what you will get. And if you're looking at less than or equal to 2, then this everything stays the same. except for this part. You're going to put in true. Okay. And if you're looking at a range, and again, if we're looking at a range, say we're looking at B. There are two ways of doing this. First, you can do binomial, binom dot list dot range. I mean, this is the easiest way to go. And it was NP, and you put in the two values. And another way of doing this is using the function above. Then it's going to be binomial dot list. Okay, so you will put in B, comma N, P true, and then subtract binom. Here it's going to be A minus 1 and P true. Okay, so these sums up the formulas that we discussed, and also the normal. And for normal distribution, it's almost the same, except for a few things. So normal, it's going to be norm dot list, and here you put in x value first, mu and the sigma, and you put in true. And it's always true because whenever you put in false, it's going to give you probability x equals little x, and that this is always 0. So there is no meaning behind it if you put in normal distribution with the probability mass function. Okay, we call this probability mass function when x is equal to something, but we are not interested in that. So yeah. Okay, so now we're going to look at some examples, and I do want to see something rather interesting. Normal distribution is very, very commonly used, and people try to use ways to come back to normal distribution even if the distribution doesn't look normal. Okay, and there are some ways of doing this, like square rooting or taking the log, so on and so forth. So we are going to see how that works through Excel now. Okay, so before we do that, I forgot to mention one other thing. That is seeing if normal distribution fits the data set. Okay, and we call this checking the plausibility of a normal model. And there is a way of doing this, and we call this normal scores plot. Okay, so this is a special graph, and let's just explain what normal scores mean. Okay, the normal score it refers to an idealized sample from the standard normal distribution. Okay, and this is known as z-scores. We already know this, right? So we divide the z-scores into equal probability intervals, and so for example, if we were to draw a curve, right, we're going to divide this into same probability intervals. So it will look something like this. So all the way down until here is 0.2, 0.2, 0.2, 0.2, and 0.2. Oh, I drew one more. Okay, so just disregard this, right? Should be 5.2s because we have 1. Probability always adds up to 1, right? So this should be, here's my pen, 0.2. Alright, and we're going to take these intervals. So for example, this let's name this M1, M2, M3, and then 4. Okay, and we come up with these z-scores. Okay, and normal scores plot, we're gonna order sample data from the smallest to largest. Okay, and second, we're going to get the z-scores, the M1 through M4, and we're going to pair sample data and the z-scores. Okay, so let's just take an example. Alright, so suppose, oops. Okay, so looking at an example, say we have a sample size of 4, and the samples are the following. Okay, so example, we have 44, 68, 75, and 82. And we also have the normal scores that correspond to the sample. So this is negative 0.84, negative 0.25, 0.25, and negative 84. Okay, and these are the numbers that divide the graph into equal parts. Okay, so using this information, we're going to plot the normal score plot. Okay, so let's move on to Excel. So these are the normal scores, and we have ordered sample. Okay, so M1 is negative 0.84, negative 0.25, 0.25, and 0.84. Okay, and the order sample was 44, 68, 75, and 82. Okay, so these are the numbers, and we're going to create a scatter plot based on this. Alright, so I'm not sure why this is over here, but anyways, and what we're looking for here is a straight line. So the more linear, or the more straight the line is, the more fit the data is for the normal distribution. So essentially, we're looking for a straight line. Alright, and if there is any kind of curve, then it indicates deviance from the normality. Right? So that's something that we need to be careful of when we're discussing the normal score. So if you were to ask if I'm not sure if this is the right model for this set of data, then you would have to do this testing. So normal score plot and see if it's right. Okay. Alright, so I did wanted to show you one other thing before we finish off today, and that was no. Okay. Alright, so let's look at this set. See, okay, this set of data. Alright, so say that these are the x values, and there are too many of them. Anyways, that's not that important. So these are the x values, right? And we want to see if this is right. If we want to visualize this, right? We want to make a histogram out of this. Then I'm sorry, let's not use this data. Yeah, let's use this one. Okay, so then you would have to create a histogram based on this, right? But before we do that, let's just look at the minimum and the maximum values so we see what the range is. So minimum of this is okay, negative 19, and max is $72. Alright, so let's just make it so you have to create a bin range. Remember that part from histogram? So let's create a bin range. And it's going to be from negative 20, negative 10. Or we can do it smaller, because this is not what we're doing, right? You just drag it down to, I would say, 75. Okay, so this is a bin range, and we're going to create a histogram. So go to data, and this thing, data analysis tool pack. Let's go to histogram. Right, so input range is already in, and just have to add one more. Okay, and bin range is this, right? And select OK, and it's going to give you the frequency and everything, right? So if you drag this and create a histogram. Oh, I don't know what. Okay, that's not it. Just select the frequency. I think I made a mistake. So insert, go to histogram, and this is the histogram that you see. And we might want to change this. So select data and just change the horizontal axis part. You can just select the bin range, and you press OK, and it gives you a nice curve. This is a bell curve, right? And we can visualize this. So this is a really good way to see if this is a normal distribution or not at a first glance. So whenever you have a set of data, first thing you want to see is the graph, right? Because you don't want to see anything else. Like, you want to see how it looks like, and you can determine from there. So this is how you can create a histogram based on the data that we have. Okay, so I would say this is it for today. I will have classwork for you guys, so if you do have a chance to look over this, just do the classwork together in class, and just give me any kind of questions you might have. Okay, so alright,